Well, good afternoon. Hi, everyone. Welcome back. Thank you so much for joining us for our second session in this winter series of bite-sized corrosion conversations. Although the weather may be wintry, today's conversation most certainly will not be. Last week, Neil kicked off this winter season with a discussion about the selection of coatings, kind of how to choose what you need. Today, we're going to heat things up a little as we welcome our first bite-sized corrosion guest, Ben van Wyk. Ben is the engineering manager at Stonecore and has gained valuable experience in the field of industrial coatings and linings, and he has a special interest in fire protection and intumescent coatings. So welcome, Ben, and really it's over to you now to share with us when and how we should choose this special class of coatings.
Thank you, Vanessa, for that introduction. I hope you guys can all see the screen that I'm sharing here. Just before I kick off, thank you to, again, to Rachel and Vanessa, and also Neil for organizing these sessions and for allowing me to be a part of this today, to share with you a little bit on something different, fireproofing coatings for the protection of structural steel in commercial and industrial applications. So just as an introduction, why does steel require fireproofing? So it might be a little bit obvious. In engineering terms, we have a reduction in yield strength and stiffness, Young's modulus, to make it even more complicated, as the temperature of our steel increases, which basically means there's a reduction in strength of the steel as the temperature increases. Okay, so it's not that important to know that the steel will melt at about 1,600 degrees Celsius. What is quite important to know when looking at these coatings is that if our steel element in our frame is heavily loaded, it's got a lot of stress, that element is going to fail at around about 550 degrees Celsius. So we would have to limit the temperature of that beam or column to 550. If our element is only lightly loaded, in other words, it's not carrying much, it will only fail at a higher temperature, typically around 750 or 800 degrees Celsius. So the first question that I always ask people when I do this talk is, who do you think is the responsible person on the professional team when it comes to the topic of coatings for the fire protection of structural steelwork? One of the answers that I often get is that it's the fire engineer who's responsible. So that's just a bit of a misconception that I want to clear up right in the beginning of this presentation. The fire engineer is involved. The fire engineer looks at the building code, and he's going to determine how long it's going to take to evacuate that building. Okay, but the structural engineer is the person who needs to keep the building standing and who has to implement some kind of coating system to achieve that. So there is a small involvement from the fire engineer, but ultimately this is a structural engineering application. In fireproofing, we split things up into commercial and industrial applications. Our commercial fires, like everything in engineering, we standardize these. So if it's a commercial building, we are dealing with burning construction materials, so just furniture, curtains, that sort of thing. We standardize a commercial fire as a time-temperature relationship, more or less per this light blue line at the bottom here. Any commercial building, doesn't matter if it's a school or a hospital or a warehouse, we assume that the time-temperature rise of the fire in that building is going to follow a distribution per this light blue line over here. Okay, that's commercial fireproofing. Industrial fireproofing, industrial, maybe a bit of a misnomer. This is actually for oil and gas, petrochem type projects where we have burning fuel type scenarios. Here we have different types of exposures. We could have pool fires. This is typically for leakage of a flammable material into a bund, and that gets set alight. That's a different time temperature relationship per the dark blue and green line over here. So a sharper increase in temperature with time. We have jet fires. Those are for burning compressed fuels. Again, even a more harsh exposure, a sharper increase in temperature with time. And lastly, we have cryogenic exposures, normally on our LNG type facilities where we have the spillage of cryogenic liquids. That's a drop in temperature and then an increase in temperature, so handled a little bit differently. So just to summarize, commercial fireproofing, we only ever have one fire that we look at from a design perspective on commercial buildings. Industrial fireproofing, 3 exposure types: pool fires, jet fires, and cryogenic spills. Just one quick slide on structural engineering in a fire. And again, just to address the misconception that this is a fire engineering issue. So we'll just briefly chat about the theory and what we are ultimately doing from an engineering perspective, the application of these coatings that we're going to talk about later, our intumescent paints and our cementitious fireproofing. In this scenario over here, we have two beams. They're the same size and they're spanning the same distance. Underneath these two beams, we have our standard commercial fire, which we said is time-temperature relationship per the light blue line at the bottom here. If you go zoom in on that, you'll see it's around about 925 degrees Celsius after an hour and around about 1,000 degrees Celsius after 2 hours. Which of these two beams fails first? The beam with the elephant is going to fail first. Okay, it's highly stressed. It's got less residual capacity to accommodate a further reduction in strength as that temperature increases. So the beam with the elephants fails first. Which beam fails at a higher temperature? That's the one with the feather. We said initially, if our elements are highly loaded, they'll fail at about 550 degrees Celsius. If they're lightly loaded, they'll fail at about 800 degrees Celsius. So the beam with the feather fails at a higher temperature. And then this last point is really so fundamental and important. So if you don't take anything else away from this talk, this should just be the one thing. What are we achieving with these coatings, again, that we're going to be discussing for the rest of the presentation? Right, so we are limiting the temperature in our steelwork to its design or failure temperature. So in this case, 800, or in this case, 550, while the temperature in the building is considerably hotter than that. Okay, so a 2-hour fire rating for this beam means that we need to keep the temperature in the beam to 550 degrees Celsius, while the temperature in the building is 1,000 degrees Celsius after 2 hours. A 1-hour rating for this beam means we need to keep this beam to 800 degrees Celsius after 1 hour, when the temperature in the building is 925 degrees Celsius. So again, really fundamental. Just lastly, on the theory side, typically our engineers in South Africa don't worry about all of this stuff about different temperatures. If we know that all of our elements fail at 550 degrees Celsius, if they are very, very highly loaded, we know that if we limit the temperature of all of our elements to 550 degrees Celsius, we will have a safe design. So normally in South Africa, our engineers won't look at actual loads or stresses in the elements or the different capacities. They will just assume that all of our elements are in a highly loaded condition, and we will just limit everything to the same temperature, normally about 550 degrees Celsius for commercial projects, and it could be a little bit lower for industrial petrochem projects. One very important thing that we also see a little bit misunderstood in the industry is how thick we need to apply these fireproofing coatings, whether they be cementitious sprays or intumescent paints. The first factor and the most important factor that affects how thick we need to apply these coatings is what's known as a heated perimeter to area ratio. Okay, and that varies with section size. It's simply the perimeter of a section divided by its area. So a slender cross section like this one will have a high HP/A ratio. It's got a large perimeter and a small area, which means it will heat up more quickly than a stockier section, as in this case, which has a smaller perimeter and a larger area, and thus a lower HP/A ratio. The net result is, if we want to limit both of these sections to the same temperature, we need to apply a much thicker fireproofing coating to our slender sections than onto our stockier sections. The knock-on effect of that is that each section on our project, each different section size, is going to have a different coating thickness, different thickness of intumescent paint or cementitious spray, and also that we need the section sizes to be able to produce accurate budgets, and that we have to explain to our clients all the time when we get inquiries. The thickness of our coating is also going to depend on the temperature that we're limiting our steel to in the context of that engineering design we've just looked at, the amount of time we're limiting it for, and the type of member. For our different products, then we have these various different tables, and on these tables, I'll just quickly run you through how this works. 4 different section factors, which, like we said, correspond to different section sizes. I've just listed those on the left-hand side here. You'll see as the section gets bigger and stockier, the section factor reduces. This table is for 2-hour ratings. We have different temperatures, and then we have various thicknesses of coating. So what this table is telling me is if I have a 203 by 46H section and I want to limit it to 550 degrees Celsius, which again is the typical design temperature, for 2 hours, I would need to apply 3,600 microns of this specific intumescent paint to that steel member to limit it to that temperature. If I've got a 254 by 73 H section on this same project and I need to limit it to the same temperature, this table is telling me I need to apply 3,200 microns of this intumescent paint onto that 254 by 73 H section. So we're applying quite thick coatings of materials. Normally for decorative paints or even sort of most corrosion systems, we're talking about 3 millimeters, so 10 times the thickness of sort of a typical corrosion type of system. Because we have all these different section sizes, your specification on a project, which we will take a look at in a sec, should always be accompanied by something like this, which is a thickness table, sometimes called a loading table in the industry. So this should always accompany your specification, some table where we've listed all the different section sizes, and most importantly, the DFT or dry film thickness that we need to apply to each different section size to achieve our fireproofing rating. In this case, 90 minutes, and here the temperatures are given. So very important that you have a table which lists all the different sections and each of their individual coating thicknesses, which we said will vary according to section size. And also importantly, that this is controlled during application. Obviously, this is a tricky thing to get right. Quality control is a very important aspect of these types of systems. We just mentioned our project specifications. Any talk about industrial coatings is going to, at some point, talk about a project spec. I know a lot of the talks that Neil and Vanessa do, a slide or two on this, so this is certainly no different. In terms of our fireproofing, on our project specifications, as per usual, it's quite important that we define a couple of parameters, including our environment, typically tied to something like ISO 12944, which many of you will be familiar with. C1, least corrosive, to C5, the most highly corrosive. That's going to impact the type of system that we use. Very important that we do the right surface preparation. We apply the right primer type and thickness, our top coat type and thickness. That has to be compatible with the fireproofing that we use. The fireproofing type should be on the specification, the thickness on something like that table on the previous slide, and then also just the application method of all of those should clearly be stated on your project specification somewhere. Now looking at some specific type of products or systems that you could look at using, we split things up into commercial and industrial fireproofing. Similarly, we split things up in terms of our coatings into cementitious and intumescent type coatings. Our cementitious coatings are normally some type of Portland cement mixed with something like gypsum or vermiculite. It's an optimization of what used to be done historically, which was just to encase everything in mass concrete. It's typically a bag of powder mixed with water on site, either spray or trowel applied in the shop or in the field. The mechanism by which these coatings work, there's sort of microscopic particles of water trapped in that cement film. When it heats up, those are released to form a steam layer, which insulates the steel from the effects of the fire and controls the temperature to whatever we need, that temperature we need to control it to. On the other hand, we have intumescent coatings. These are now water-based, solvent-based, or epoxies normally, basically paints and applied as such. They operate by a different mechanism. There's a chemical reaction which causes these types of paints to swell up or intumesce in a fire scenario, anything from sort of 10 to even 50 times the original thickness. And that forms what is known as a heat-blocking char, which again insulates the steel and controls the temperature for us. In America, they call the cements SFRMs, spray applied fire resistive materials. They call the intumescent coatings IFRMs, but normally PFP or passive fireproofing is just sort of used as a generic term to describe any type of fireproofing coating, whether it be intumescent or cementitious. So those are broadly your sort of two options. In addition to that, there are also various gypsum, calcium silicate boarding type systems. They operate sort of in the same way, but because they're not coatings, we're not really going to talk about them. Just in terms of petrochemical fireproofing, there's a lot of scope for fireproofing on our petrochemical oil and gas type projects. It's not just about evacuating the site like on our commercial buildings. We're actually also preserving the infrastructure. These plants are hell of expensive to build, as you can imagine, and quite prone to fires because of all the flammable materials. So we don't want our pipe racks and all of our stuff to be irreparably damaged. We want to preserve that infrastructure for our owners. In terms of typically what gets fireproofed on these petrochemical oil and gas type projects, a lot of the structural steel, many of the pipe racks, many of the storage vessels, a lot of the supports for our mechanical equipment, including legs for spheres is a very typical application, tower skirts, vessel skirts, all kinds of equipment supports, as well as our equipment cables. Those coatings are a little bit different, but in terms of our structural steel and certainly our vessels and our supports, that's all done with these types of coatings that we have been discussing. Your owner specifications are quite often going to govern and tell you exactly what they want fireproofed on their facilities. The Sasol fireproofing spec, which you can go take a look at, SP0022A, is quite a good example of that. So on these petrochemical type projects, again, we have cementitious coatings options and intumescent options. Our cementitious coatings for these petrochem projects are what's called high density cementitious coatings. These are normally about 750 to 1,150 kilogram per cubic meter, so about a third to a half of the weight of normal concrete, either spray or trowel applied. What's quite nice about these systems is we said we have different exposure types, pool fires, jet fires, cryogenic spills. With a lot of these products, they'll give you combined protection in one system to all three of those exposure types. You don't have to go split your plants up into different areas, split your fireproofing scope up. You apply these and you know you are good to go in terms of all the possible exposures on that plant. In terms of advantages, they are easier to apply and much more cost effective than the epoxy alternatives, the intumescent paint alternatives, but on the downside, they are a bit more bulky and a little bit more prone to damage if applied off-site and transported. Because we normally have a mesh to make sure that these cements bond properly onto the steelwork, you can choose if you want to apply these in a contour following the profile of the steelwork or as a box design. This will either be for you as EPCM to define or from the client. The box designs reduce the amount of fireproofing and it's a slightly better insulating system. So this is what we would normally suggest if the client doesn't have a preference. Just a quick note on corrosion under fireproofing. This is actually a similar type of application to corrosion under insulation, where you can have a highly corrosive microenvironment building up under these cements. It's also hidden from sight, so this was historically a bit of a problem before people started to take cognizance of this. So just be aware that you do need a properly designed corrosion specification underneath your cementitious fireproofing. We did see some failures like this historically, which was obviously quite a disaster, but this is easily avoided by application of the correct system. So just be at a high level aware of this, and that whoever is applying the cementitious fireproofing is also designing a proper corrosion system for that fireproofing, so you can avoid this type of situation. Here's just some pictures of trowel application in a fabrication yard. So this will be applied off-site and erected with the cementitious fireproofing already on the steelwork. And here they've meshed the structure up on-site, so this will be an in situ application. So again, can be done either way. Here's an example of a contour design, again, following the profile of the steel section, and this is an example of a box design. So I've actually walked around in Sasol and thought something was a concrete column because of this rectangular nature, but it's actually a steel column that's been fireproofed in this case. Okay, lastly, we have our epoxy intumescent coatings. We said we have sort of water-based, solvent-based, and epoxies. The water-based and solvent-based bases are normally used for commercial applications. On our petrochemical facilities, we skip those. We just go straight to the Rolls-Royce type products, which is what these are. Our epoxy intumescent industrial coatings. These really are sort of the peak of the technology as it's been developed. Best physical properties, quick and easy to apply, less maintenance. They don't weigh as much as the cement, so these are also what are used in offshore installations and applications. They don't get damaged as much when transporting, so we prefer these for off-site application, unless you have a cement that has been proven to handle that. On the downside, obviously very costly in materials and application, and some of these products can have different capabilities in terms of those exposure conditions. So you might need a certain type of epoxy for a pool fire and a different type of epoxy for a jet fire, just something to be aware of. In terms of these epoxies and corrosion, not as much of an issue as with our cementitious fireproofing. This is an epoxy. We're putting it on at about 10 to 12 millimeters thick. So normally, as long as we have a compatible primer and top coat, we are happy that we will get a C5 specification out of that system. Here's just a picture of a typical epoxy intumescent installation on a petrochemical facility, and some pictures of spray application in a fab shop. And in this one, normally we have a fiberglass mesh or a carbon fiber mesh somewhere inside that epoxy system. Here the guys are rolling that in at a half or a third of the way into the depth of the coating with rollers, and then they'll put the final coat of epoxy intumescent over that. Okay, just some ballpark cost figures here, just to give you guys an idea. Decorative paint, we're normally looking at about 80 to 100 Rand per square. Material and application of these systems we've just looked at, around about 2,000 Rand a square for our cementitious system and about 5,000 Rand a square for our intumescent system. So very, very expensive systems on our petrochemical facilities. And again, for that reason, quite an important thing to understand and develop properly in terms of the specification and design. On our commercial projects, just to compare, our commercial cementitious system is typically a lower density cement, normally around 250 Rand per square for 1 hour rating and 450, 500 Rand a square for 2 hour ratings. Our intumescent paints in commercial applications, about 250 Rand a square for 1 hour ratings, which is interesting, about the same cost as a cement, and about 1,700 to 2,000 Rand a square for 2 hour ratings. So this sort of is where costs can run amok a little bit and wreak havoc on commercial projects. All right, just a quick summary of what we've covered today. We said in the beginning, the conception that this is purely fire engineering is just that, a misconception. Structural steelwork fireproofing purely is a structural engineering issue. We looked at some of those details. I encourage everyone I talk to sort out all of these design and specification issues in as early a phase of your project as possible. We saw that cementitious systems are more cost effective than intumescent systems, although our intumescent systems are higher performance and also suitable for offshore work. We need to make sure everything is compatible, especially in terms of our primers and top coats, with our fireproofing and project corrosion specification. We need to ensure our designs are to an appropriate critical temperature. And last but not least, be aware of budgetary issues that can and do arise from ill-considered system selection and design. Lastly, if there's any of this that you guys want to discuss in more detail, you feel free to contact me. There are various other forms of courses and talks available that we can do in that case. That's all from my side. I'll hand back over to Vanessa. Thank you guys for your time.
Wow, Ben, thank you so much. This really is such a topical discussion point, certainly for me personally. I think I mentioned last week that our local grocery store burned down, and about 3 days ago, a home not far from mine in our neighborhood also burnt down. And fireproofing really is not something I've ever considered, which is quite remiss of me. There are a couple of questions, Ben, that have come through, and I think maybe we can take a couple of them now. So if we just very quickly look in light of our discussions about ISO 129 that we had in March, and also Neil's comments last week, do fireproofing systems fit easily into the standard? You did make a little bit of a reference to it, but do they fit in easily?
Yes, they do. So normally the environmental category will just drive what type of system we use. So if it's low corrosion C1 sort of to C3, typically a water-based system. If it's C5, even in commercial applications, normally we'd go with an epoxy. So the corrosivity environment will drive what type of fireproofing we use, and it will also generally drive what top coating system we use to protect that fireproofing underneath. So it is a very important design consideration, but something that is very easily incorporated into the design.
Cool. Now, the question that's come in is, typically, how would you assess during a maintenance inspection for CUF? Would you do NDT inspection? Would that be kind of the primary way of undertaking an inspection?
I'm not sure if there are any NDT sort of approaches that are available. I would think you would probably have to do something destructive, especially seeing as we're dealing with those cements. They are quite easy to patch up. So I would maybe identify sort of a regime and say, look, every 200 squares, we need to do two patches, break a piece out, check. Can be patched up very easily. So I would assume it would be a destructive sort of thing that you would have to do.
Cool. Now, associated with that, obviously there are costs, but also just the costs of this fireproofing are a little mind-blowing. Are there any ways that one can can optimize the costs at all?
Yes, so we looked in the beginning at different temperatures and the fact that we design everything for a worst case condition. We design all of our steel as if it's under that elephant loading condition, whereas that's not really the case. So if we need to optimize, if there are cost issues, then we go look at what the actual stresses in the actual members are and what their actual failure temperatures are, and we coat them accordingly. So we reduce the thickness of the coating by designing for higher temperatures according to the actual stresses in our members. And there's some significant cost savings that you can achieve by doing that. You do need the structural engineer's input though, which the guys aren't always too thrilled about.
There are, gosh, a number of questions. There's another one about galvanizing. Obviously, galvanizing is used extensively. Can fireproofing be used over galvanized surfaces?
Yes, so with our intumescent paints, commercially and industrially, we normally just require a tie coat of our galvanizing. It's not an expensive component, but we would probably prefer something that we know sticks to the galvanizing and to the fireproofing. With our cements, some of them will go directly over. Some of them would even beef up the galvanizing with those cementitious systems because of that CUF issue again. So it's kind of a case-by-case basis. Intumescent paints generally with a tie coat, the cements we sort of look at again on a case-by-case basis.
It's like all these things. There's no one option fits every scenario, and that's why we need experts like yourself. Hopefully the new knowledge that you've gained, certainly that I've gained, has made today's experience quite palatable. Thank you, everyone.